Hello everyone. In the previous video, you learned how to build and simulate a boost converter in OpenLoop. In this video, you will learn how to add a controller for this boost converter. We are still working on the same example as the previous one. So here we have the controller block diagram. We have an outer loop controller for the voltage and an inner loop controller for the current. The controller takes as inputs the desired output voltage, which is a constant value, the measured output voltage, which we are measuring on the load, and we have also the measured inductor current that we are taking from the current measurement block here. So to start, we first need a constant block. The constant block can be found in sources. This is the constant block. You double click on it to set the desired output voltage, which is 36. And then we need the summation block, which can be found in math operations. This is our summation block that we can use to add or subtract inputs. You double click on it. In this case, we are subtracting the measured output voltage from the desired output voltage. We need to change this plus to minus. So it takes plus 36 volts and minus the measured output voltage, and then it feeds it to the PI controller. Now, the PI block can be found in continuous. This is our PID block. We double click on the PID block. And what we want for this case is just a PI controller. So we select PI controller from the drop-down list. And we set the proportional gain and the integral gain. For this case, I will put the proportional gain to be 0.4 and the integral gain to be 80. These are the same values I already have here. We add another summation block and another PI controller with the same values also. And then the output of this PI controller will be the duty cycle of the switching pattern of this MOSFET. But the duty cycle should be limited. It should be bounded between 10% and 90%, for example. To do that, we use the saturation block. So the saturation block can be found in commonly used blocks. This is the saturation block. We double click on it to set the upper limit and the lower limit. So we set this to 0.1 and this to the upper limit should be 0.9 and the lower limit should be 0.1, and this is equivalent to 10% and 90%. After that, we need to generate a PWM with the duty cycle being input to it. The PWM generator can be found under the power electronics section, pulse and signal generators, and this is our PWM generator DC-DC. So this block outputs the pulse to the electronic switch of a DC-DC converter. The input D is the duty cycle that determines the percentage of the pulse period that the output P is on. The switching frequency is the only thing we need to set, which is 150 kilohertz for our example. After setting the switching frequency, the output of this block will be a PWM with a duty cycle coming from the controller and a switching frequency of 150 kilohertz, and we send this to our MOSFET. Now I will run the Simulink file and check the results. So we have in yellow the output voltage and in blue the inductor current. As we can see, the output voltage has achieved the desired steady state value, which is 36. The reason we are having exact 36 is that we are using a PI controller. I'm gonna stop this for now. If we want to see the output voltage and the inductor currents in separate plots, we can do that by changing the layout of the scope. So I want two plots stacked vertically, and that's it. So we have here the output voltage in the first plot and the inductor current in the second plot. You can also add in the Simulink workspace a text annotation by simply double-clicking. This is a two-loop controller for my boost converter. And then I click on Add Annotation. You can also add an area annotation the same way I did here. So for example, I will add it here, plots. And when I create an area annotation and I move it, I will be moving all the blocks inside it. And that's it for the two-loop controller for the boost converter.